So we want to now explore the concept of angular momentum. And this is the next natural progression in our discussion. If you recall, when we were talking about our linear quantities, after we introduced the concepts of velocity and acceleration, we then looked at force, and then we looked at energy, and then momentum. Well, in our rotational analysis, we've introduced the ideas of angular displacement, angular velocity, angular acceleration. Then we introduced the idea of torque, which is the rotational analog of force, and then we talked about rotational kinetic energy in the last video. So now we need to talk about the next step in the progression, angular momentum. And angular momentum, L, all right, we denote it as the letter L, and it is equal to the moment of inertia times the angular velocity. And you might have been able to deduce that this was going to be the case, as we've had the nice analog between the rotational kinematics and the linear kinematics, just replacing any of the linear quantities by their rotational analogs. And if you recall, the linear momentum, P, is equal to mv, P is equal to mv, and what this is saying is that the linear momentum of an object is equal to the product of two quantities, its inertial quantity times a dynamic quantity, in this case the velocity. All right? So an inertial quantity times a dynamic velocity, or dynamic quantity, if you will. And the angular momentum is going to follow the same recipe. And in the rotational cases, we've been replacing V's with omegas, A's with alphas, and M's with I's. So I is the inertial term, and omega is the dynamical quantity, all right? And so these follow logically one from another. And you may then also have the thought, well, perhaps is angular momentum related to torque in the same way that force is related to momentum. So also remember that we described force as equal to the time derivative of an object's momentum. And you may have the thought, well, if F is equal to dp dt, then is it possible that torque is equal to the time derivative of angular momentum? And indeed, that actually is the case. And we'll show you how that works. Right now, for starters, recall that we have these definitions of torque, okay? Torque is equal to the force times a moment arm and the sine of the angle between them to pick out the perpendicular component. Or torque is equal to an object's moment of inertia times the angular acceleration it's experiencing. And torque is also equal to the cross product of a moment arm multiplied by the force. And in fact, these two definitions right here are essentially the exact same thing. Even though all three definitions are equivalent, these two are saying the exact same thing, because if you remember, a cross product is equal to the magnitude of A times the magnitude of B times the sine of the angle between them. So if I have R cross F, then it's the magnitude of R times the magnitude of F times the sine of the angle. But if you look at this definition of torque, recall that alpha is equal to d omega dt, right? So torque is equal to I times d omega dt. And this is analogous to Newton's second law. For a constant mass, this works for a constant moment of inertia. F equals m dv dt, and this is nothing but F equals ma, right? This is nothing but F equals ma, and so the rotational analog is this, okay? We can also see that from the definition of torque in the cross product form. Okay? It turns out that if you're looking at angular momentum in its vector form, okay, in its vector form, this is the magnitude form, or the scalar form, if you will, but technically angular momentum is a vector, and it is defined as the cross product between an object's moment arm about the axis of which it's rotating, multiplied by its linear or tangential momentum. Okay, so L equals R cross P. Now, If I take the time derivative of this quantity, then I have to take the time derivative of the total cross product and as you can see, what that means is that if I take the time derivative through, it's not just the time derivative of the moment arm multiplied by the time derivative of the momentum, or crossed into the momentum, as these are still vectors. What I have to do is take the time derivative of the moment arm, cross that into the momentum, and then I cross the moment arm into the time derivative of the momentum. This is a chain rule or product rule process here. So what we're going to do is take the moment arm multiplied by the time derivative of the momentum, and then I add to that the time derivative of the moment arm crossed into the momentum. Okay, so this is the total time derivative of the cross product of the angular momentum. Now, a couple interesting things happen here. This dr dt is nothing but the linear velocity of the object, or the tangential velocity, right? Dr dt, distance over time, the time derivative of an object's displacement, is nothing but v. So this becomes v cross p. Okay, so that's v cross p. But imagine an object that is traveling in a circular path. Okay, and the circle is just the easiest path to visualize this for, but it works for any curve. If I have an object, let's say my object is rotating about this circle here, and let's say that my object is moving this way, right? So maybe you're talking about a rock tied to a string that's swinging above your head, whatever the case may be. At this particular point, if it's moving in this counterclockwise motion, then its instantaneous momentum is pointing tangential to the circle, but its velocity must be in the same direction as its momentum. Its instantaneous velocity must be in the same direction as its momentum. So this arrow contains the direction for both P and V. And so these two are parallel, and the cross product of a parallel quantities goes away. So the cross product of V cross P actually goes to 0 by virtue of the fact that those vectors are parallel. And remember that the cross product picks out the sine component. So if they're parallel, then the angle between them is 0, or 180 if they're anti-parallel, and the sine of 0 or 180, either one, is 0. So this term goes to 0. So we're just left with this form right here. But what is this? Well, dp dt, we've seen that before. That's nothing but force, right? This is nothing but the force that is exerting the torque across the lever arm. But this is exactly the definition of torque. Torque is R cross F, and that's exactly what we obtain here. So torque is indeed equal to the time derivative of angular momentum. Okay? Torque is equal to time derivative of the angular momentum. So now we actually have 4 potential definitions of torque that we have to take into account. Torque can be Fr sine theta, I alpha, R cross F, or torque can be considered as the time derivative of the angular momentum of an object. And in fact, it can be any of those, okay? And they're all equivalent. If it's one, it's all of the others, but which one you use mathematically is going to depend on your situation. And just to kind of give you a sense of some of the differences between these, okay, you would use this if you have a force moved across a lever arm and you're trying to rotate an object about that lever arm, about an axis. And if your force and lever arm are not perpendicular, then you would just take the sine of the angle, whatever that angle may be. If you have an object, like maybe a sphere, a cylinder, a rod, something with a nice moment of inertia from the table in the book, and you apply some sort of torque to it, then it's going to cause that object to have some angular acceleration. So if you're given the torque in the moment of inertia, you can get the angular acceleration. Or if you're given an object and its moment of inertia, and you're told that it has some sort of angular acceleration and you're asked to find the torque, then this is going to be the easiest equation to use. If you're given a lever arm and a force in vector form, okay, and you're actually explicitly asked to use the cross product, then this is the form that you would use. And remember, the cross product is the determinant of that 3x3 matrix that we showed you. And then if you're given an object's moment of inertia and you're given its initial angular momentum and you're told that the angular momentum somehow changes with respect to time, you can take the derivative of the angular momentum with respect to time and you can find the torque that way. So all of these definitions are in fact equivalent, but which one you would use is going to depend on the situation you're given. Okay, so that's a basic introduction to angular momentum and how it's related to torque. In the next video, we'll actually do some examples with the conservation of angular momentum and see how to actually apply it.